new lecture. We just quickly review what we have done last week. Let me write over here. So if cosine A. Okay, if this is my message for FM signal, we have A cosine omega CT plus beta sine omega MT. Right? The last time we go through step by step. And cosine angle 1 plus another angle we can write down as A cosine beta sine omega MT. Okay, and last time we talked about if beta is small, beta less than 0.2. This equation can be written as narrowband FM. Okay, so when beta less than 0.2, this whole term is approximately equal to 1, right? And sine a small number close to the one in the brace. So sine this one close to beta sine omega m of t. So we have this narrowband FM. Today we talk about if beta is a big number, not less than 0.2, what can we do? So how about okay, how about beta is greater than 0.2? So my signal will be much more. No, that's okay. So this equation is this one, right? Before we explained it. Okay, here. So we have cosine minus sine, right? We have one angle plus another one. So we have cosine 1 and cosine another one minus sine 1 times sine another one. Okay, so here, cosine beta sine omega m of t, when beta is not a small number, it's no longer close to 1. It is something like this, very complicated. It can be expressed by unlimited summation of many harmonics. And each harmonics amplitude we use basal function. So my cosine beta sine omega m t is something like this, right? And sine beta sine omega m of t is also unlimited summation of another harmonics, right? Many other harmonics with different frequency. The amplitude also determined by basal function. So here we have n is which harmonic, beta is your modulation index. So different beta, we have different value, right, for basal function. So your signal will look like many harmonics combination, right? And each one's amplitude is determined by your beta. Very soon we show some examples. So just remember, the new equation for bigger beta will be much more complicated. Okay, any problem for this picture? How can we get? So this is only for sinusoid as your message, right? If your signal is no sinusoid, the expression will be even more complicated. For Bessel function is integral of complex exponential. However, you don't have to calculate this one, right? We have a table from our textbook and also from other reference book. So Bessel function, you don't have to calculate, right, this integral. In our textbook, we have a table, and this table you are going to use in your little homework and the final exams. So this function table, you can find on the textbook, right? If you don't have this one, some other reference book will also have this function.
What appendix is it? What appendix?
Number G for George. And function table. Page 735. 735. Okay, so this is Bessel function. And we combine, right? We combine here this cosine and sine term, let them together. So we have, this is when A0 actually will be your carrier, right? Your carrier. Here, omega C plus N omega M will be harmonics, right? Away from your omega C, right? Bigger N a little further away, right? Smaller N will be closer to your fundamental carrier frequency. So I have unlimited sideband or unlimited harmonics around omega C. How big it is, right, depending on your original amplitude for carrier, also Bessel function. And I'm going to show you. Okay, let's look at one. Over here. So this is an example for what does a sinusoid modulated FM signal look like. So when beta is a very small number, right, we have a carrier and pretty small sideband 1, right, first. So this is omega C plus omega M. So this is when beta very small. So narrow band close to AN. When beta is a little bigger, right, we have more sideband up here around the omega C. So here, when beta is 1, is a little wider, right? When beta equals 5, you have more harmonics, and beta equals 10, even more. And beta 5 is the standard FM radio broadcast. Choose beta equals 5 as the index. So this bandwidth compared with original signal's bandwidth, right, much wider, much wider. So now we go back, right, go back to the equations. Okay, Bessel function is even symmetric. So we combine previous equation, and odd and even, we combine them together. We have this one. Okay, please, please remember this one. And you're going to use, right, in your homework exams. For wideband FM signal, it can be viewed as many harmonics, right? With different amplitude. The amplitude is determined by Bessel function. N is which sideband, how far from omega c. Beta is the multiplication index you choose. Okay, so this one, the highlight one, please remember it. Okay, so Bessel function can be also found from the curves. So we can find Bessel function, each one, right, can oscillate, similar to sinusoid, but the amplitude drops. Similar to sinc function, right? One set of sinc function. So this is when n equals 0, when n equals 1, 2, 3, 4, 10. Okay, and here, n is rich harmonic, right? And beta will be, beta will be here, right? This is new beta. Okay, so from curves or from table. Here will be n, right? Will be n, and inside this brace is your beta. For example, right, when n equals to 0, right, beta equals 3, we have 0.02 as a Bessel function value. Okay, we showed this picture before. So now we can find with different beta, my signal different, right? One difference is we have different bandwidth depending on value of beta. Second, the power allocation is also changing, right? Here, most power allocated on the carrier, right? And here we find carrier kind of drop, but more power go to your four sideband here and over here. So you can use different beta, adjust each harmonic's power. So this this method give you more flexibility. For example, you have a very strong interference, right? Over here, so I can allocate my power into other sideband, right? So we can avoid this kind of very high jam of interference. Turns out my performance compared with AM much better. Right? You can hear that the difference. So we'll have two important things will be discussed later. One is how can we find the bandwidth associated with different beta. Second, the power allocation for each sideband. Okay, so this can say that, okay, we leave it later. Here, just copy from our textbook. For FM video broadcast, So channel, right? You know when you tune the carrier frequency. The non-commercialized station, channel 201 to channel 200. So 88.1 megahertz to 91.9 megahertz. Each station occupy around 200 kilohertz. So the bandwidth is much wider compared with our AM broadcast. Commercialized station 92.1 to 107.9. Okay. Peak frequency deviation 75 kilohertz. So you're away from your center frequency about 75. However, the bandwidth is 200, right? So you have some guard between one station and another one. Beta is 5. Beta is 5. Okay, so this is just all the parameters, right? People use for broadcast. Any questions so far? So now we talk about first important thing, power allocation for each sideband. Okay, this slide is simple. This is my FM signal, right? The mean square value or total power. The mean square value of FM signal is half A square. Half also, comes from the cosine. So this one is easy, right? This one is easy, depending only on the carrier signal's amplitude. Two others. All other sideband, we rewrite it right in basic function format. So you will have many different harmonics. So for different harmonic, the mean square value of each sideband is over here. So we have half A square from here, right? Jn beta square from here, right? Half actually from the cosine, here. So this is mean square value for each sideband. When you calculate this one, you need to choose which band, right, and find what is beta you use in this signal. And we are going to show some examples. Okay, we are going to use this one as an example. So in previous example, we kind of have some feeling, right? Power changing, right? Bandwidth is also changing. So for this exercise, let's go over. Okay, we just copy previous equation, right? My signal is cosine omega z plus beta sine omega m here. We have a FM signal. Try to find the average power, the mean square value, and the power at carrier frequency for different beta. So the two equations we are going to use will be sideband N, right? Okay, sideband N. Square, right? N beta square. So we are going to use those two equations. So for first one, the average power we know will be this is my average, right? Average power. So this one is straightforward, right? A is straightforward. You should be fine. Okay, now we look at the second one, the average power at carrier. So what is carrier? Carrier means no sideband, right? No sideband. So for carrier. Okay, carrier means n equal 0. N equal 0. So PC, right? P0 half A square J. Okay, will be half A square J0. Beta square, and beta will be 0.5, right? 1.0, 2.4, 2.5, and 4.0. So if you check your table, right, find J0 beta, you can find the power. And if you look at your curve, you still can do the same thing. So let's take a look. When I have different beta, the power allocated on my carrier changing, right? Different beta, different power. Okay, not very clear. Okay. Let's go to this one. So for n equal beta, we're going to look at the first one, right? N equal 0. So we can imagine, right, at first, pretty high power, and it is going to be smaller and smaller. Around beta equal 2.4, there's no power on my carrier, right? Look at the curve. It's going to be bigger and bigger because J and beta squared is going to be bigger again, then smaller. Okay, reach 0 one more time. So your first carrier, your carrier will be smaller, bigger, smaller, bigger, smaller, bigger. According to the curve, let's look at what is the real picture we have. So we just plot the line spectrum, so only those lines. Then beta is 0.5. This is carrier. I have 4 sideband, not very significant, right? Second sideband, pretty small. Now I increase beta. We can imagine that carrier will be dropped because J0 beta curve is decreased, right? So this one decreasing. We have smaller carrier, stronger first sideband and stronger second sideband. Now we can find the third sideband is also right appears. Now for beta equal 2.5, very small, right? Very small. We have wider band. This one dropped to a very small number because 2.5, very close to 0. So pretty high first sideband, right? Very significant second sideband, third, fourth, and fifth. So wider.
These values can be found on that chart, right?
Yes. Yeah. So J and beta you can find from a chart.
And then carrier will always have n of 0.
Yes, carrier always be 0. Yeah, carrier n be 0. You're right. Okay, beta 4.0 we have even wider. Now carrier go back, right? Go back, become bigger. So different value. When beta equal 2.4, I use another slide. So there's totally no carrier at all. Most power used for sideband information. So at this time, there's no information here, no power here. So you can change beta to adjust your bandwidth. You also adjust the power for each sideband. So this is the good thing for FM signal. Okay, any problem? This is just like a warm up. And we have our example from our textbook. So let's just repeat one more time. So when beta change, for example, beta change, right? We look at first carrier. Beta becomes bigger, my power for first carrier will be dropped. Right? Here, reach 0. Become bigger again, smaller, reach 0 again. All other sideband also same situation. So for example, here, right? Drop to 0, right? So first example, we are going to use similar thing. Or any problems for this exercise number 1. So 6.4.1 example from our textbook. Okay, so let's look at this one. We have a given FM transmitter. This signal is modulated with a single sinusoid. So FM transmitter. Sinusoid is my message. The output for no modulation is 100 watt into a 50 ohm resistor load. So the output, so that means the total power. The total power is 100 watt. Okay, equivalent to the load equivalent to a 50 ohm resistor. The peak frequency deviation of the transmitter is carefully increased. Okay, this one's a little confusing. Let's read this one, and I'm going to explain what's going on. So the peak frequency deviation of the transmitter is carefully increased from 0 until the first sideband amplitude in the output is 0. So pretty confused, right? So let us translate this one. So peak frequency deviation. Delta omega. So peak frequency deviation is increasing, means beta is increasing, right? Because omega m will be the same. You have your message determinism. This one means beta increase. So I carefully increase my modulation index, and while I observe something, right? The first sideband in the output from 0 until the first sideband in the output is 0. So let me write down my equation. Okay, xc of t is n beta cosine omega ct plus n omega m of t. Okay, so first sideband. Okay, you look at which one? J1 beta, right? Cosine omega ct plus omega m of t here. N equal 1, right? This is my first sideband, So we know first sideband is changing and beta is changing. The changing is related with my Bessel function, J1 beta.
Excuse me. When the problem says the output for no modulation is 100 watts,
Mhm.
does that mean that's the carrier's power?
Yes.
Like, okay.
Yes. Yeah, you're right.
Okay.
So increase beta, and we know sometimes the amplitude of my first band is zero. So at this time, we want to calculate. So under this condition, find average power at carrier, average power for all remaining sidebands, average power in the second order sideband. So we have to find my beta, right? My beta. Okay, last time we talked about carrier, right? Carrier is changing like this, right? Like this. So high, lower, almost gone, right? Lower, higher again. So this time we should look at n equal 1, n equal 1. So we know for J1 beta, it will start from 0, right? Go up, bigger, 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 smaller. Then it reach 1. So here give me the hint, what should be my beta? This beta, my first band, output is 0, is 0. And if you look at your table, right? If you look at your table, J1 beta, right? You look at so there is no exact number, right? Exact number. So our textbook, this. Okay, if you look at here, right, we know the number is around close to 4, right? Around 3.8, 3.9. So from our textbook, use figure 6.9 and the projection number G, we see that J0 beta equals J1 beta equals 0. Cross occurrence beta equals to 3.8. Okay, so beta, right? We know beta is 3.8 from appendix all curve, right? So beta equal to 3.8. All the sentence in this red circle tell us my modulation set beta equal to 3.8. Okay, so maybe, yeah, it's a little confusing, but just have to tell you, my beta is 3.8. Now we look at the problem 1, right? Is, carrier power of this one. I want to explain a little bit. This textbook maybe is too simple. Okay, so A, right? 6.41. So A carrier power. Here we use P C, right? P0 half A squared P J0 beta squared, right? J0 beta squared. This is PC and PT is half A squared. Total is half A squared. So we can find J. Okay. Okay, J0, 0, is 1, is 1. So if I can modify this the textbook, I'm going to change this just to 1, right? This 300 is kind of confusing. So combine those two, we get PC will be half, right? A square, J0, 3.8 square, and half A square. Is 100. The total power is 100, right? We just it's from the textbook, from the condition. So PC will be 100 times J0 3.8 square. And J0 3.8 from the table is around 0.4, minus 0.4. So my carrier power is 16.
So when you finding J of 3.8, do you just compare it to like J of 4 and really
J-
get close to that?
No, J point. So you want to check you want to look at the table.
Yeah.
So if you have table 3.8.
So when you find the beta from the J1,
Yes, yeah, because we know J1. We find beta value is 3.8 because my first sideband is 0. And I'm going to use 3.8 to find my carrier power. This is the problem asking, right? On a certain condition, the air power at carrier frequency. Let me see if I can. So if you have let me see if I can have this one. So now we look at J1, right? J1. Okay, J1, right? J1 will be this column, this row, and the 3.8, right? 3.8. J1, right? 3.8, right? No, for J0, carrier, right? So 3.8, J0 is around minus 0.4. So you use your table, Now we go back to my Okay, so power for carrier is 16 watt, 16 watt. The average power for sum of remaining sideband will be total power minus PC, right? So it's 84 watt. Okay, so, part two is easy. Part 3. This one I want to seal a little bit more compared with our textbook. So if you look at this one, carrier, there are only one carrier. But for sideband, I have omega C plus omega M, right? Omega minus omega M, here omega C plus 2 times omega C, so we have carrier. First sideband will be plus and minus. Second sideband also will be plus 2 and minus 2. So when you consider second sideband, we have both sides. both sides. That is why when we calculate the second sideband, so when we calculate second sideband, there's 2 times. Let me write this down. Second sideband will be P2 plus P minus 2, right? So I have P plus minus 2. Will be 2 times half A squared J2 beta squared, right? So second sideband should be 2. And 2 cancel, I have A squared plus J2 3.8 squared. You go to a table, find the value of it. It's around 0.4, right? Square, you get the second band. Okay, we know half A squared. Half A squared is 100 watts. So half A squared is given from the condition. My second sideband will be plus and minus, right? Plus 2, minus 2. 2 sidebands for second, third, fifth, fourth, fifth. Carry only 1.
Isn't this supposed to be 50 watts? Because since like A equals to 10.
50 watts. Which 50? So half half A squared is 100.
He's saying, should we divide by the resistor, the 50 ohms?
Or if we ask you the amplitude. Oh, I know what you mean. Oh, yeah, yeah.
Over R.
Yeah. The amplitude. So here we ask the power. If we ask amplitude, right, we have
That's only for actually for the current or voltage.
yeah. So power, right? Power should be the same, right? Power we just use 100 resistance. So if we ask about the current of P is R, right? V squared. So if we ask what is O, I know what you mean. So we don't use. How about we don't use A squared? We use P total. How about that? We use P total. Don't use A squared. Yeah, A should be yeah. Yeah, I believe you're right. But this is the solution from our textbook. So if we ask power, you consider the total power is 100 watt. Okay. So we should not use A squared. We should use maybe just the P, right? Yeah. Yeah, the 50 ohm is really confusing. Okay, so just remove it. Yeah. So we didn't use that. We didn't use 50 ohm at all. Okay, so the output from the low modulation sigma is 100 watt. Yeah, half A squared. If we use half A squared, we should consider resistor 50 ohm. But we talk about the power. So only the power R value does not matter. Okay, so this example just show how to calculate power for different sideband and how can you determine your beta index. Okay, any problem or questions else for this example?
So here it says the power for the output for no modulation is 100 watts. So is that the carrier power? That's not equal to the total power, is it? Like
Carrier power for no modulated signal, the total power is the carrier power. But when it's modulated, the power will be split, right, into different sidebands.
okay. All right. So when we're saying 100 watts, that's the carrier power, even when it's modulated?
Yeah, this is 100 watts is the power, your waveguide, right, or your transmitter send into the open air. So this is power so if you use battery, right, you know the power of your cell phone, right? Just maybe power used for transmitting, right? Power used for like your LCD, something like that. Right? Total power generally will be for FM, total power is fixed. Right? Even for your cell phone, it's smart, right? Sometimes it just can reduce the power because nobody is using it, right? So the LCD is kind of dim or you just like.
Okay, so the total power is a constant.
Yes, yeah.
But when you modulate it, the carrier power changes.
Yes.
Okay.
Yeah, the total power, you send 100 watts to your transmitter, right? That is, energy consumption for your station.
Okay.
So if you don't transmit, power is can you shut down? Yeah, I'm not sure. Can you shut down your you do not want to do that, right? Yeah, so you transmit, right? Your power will be allocated at different sideband according to beta you choose. Okay. So we talk about fourth important thing of FM signal. We're going to have some practice, and for sure, calculate power for sideband will be in your final exam. So very important. Then we talk about bandwidth. So we can start to talk about bandwidth, and we are going to show examples next time. Okay, bandwidth. So bandwidth. We know wideband FM you have unlimited bandwidth actually, right? So you have unlimited sidebands for wideband FM. Just maybe some sideband very, very small, very non-significant. Okay, theoretically bandwidth of FM is infinity, right? Infinity, really wide. And for Basal function, similar to sinc function, right? Decrease when n increase. So significant sideband is the most accurate way we define bandwidth of FM signal. So significant sideband means, right, this band, when, for this sideband n, the amplitude of this one greater than 0.01, so means the power of this sideband will be 1/10, right? 1/10,000 times compared with the entire power. If this value drop less than 0.01, we think those sidebands too small, right? We don't consider it as our valuable, right? Sideband. So this is the most accurate way we tell how wide is the bandwidth. However, this one may be a little complicated. So there are alternative way to calculate bandwidth of FM signal. Okay. So from our textbook, it divides into 3 different cases, depending on the value of beta. So for different case or different situation, different beta, you have different equation to calculate the bandwidth. Last time we talked about, right, when beta less than 0.2, we have a bandwidth 2 times of your modulating signals bandwidth. Here we add 2 more equations. One is for large beta. How large, right? Students are always asking how large. Generally will be a pretty large number. In exam, I'm going to give you, for example, 40, 50, 100. So really big number for large beta. If beta is a large number, your bandwidth is related with peak frequency deviation, right? 2 delta omega or 2 delta f. So compare with your original signal bandwidth, the bandwidth is really wide. E1 So this bandwidth actually is close to AM, right? Close to double sideband. AM's bandwidth. Okay, as we know, right, beta is delta omega over omega m, delta f over delta f over ff. So this time, my bandwidth is 2 beta times of your signal's bandwidth. So compared with AM will be bandwidth will be beta times, right, y as double sideband AM signal, when beta is the big number. The third one will be beta not so small and not very huge. The beta in between we have W will be 2 delta omega plus omega m. So then beta in between, for example, right, 1, 2, 5, all those things, your bandwidth is related with peak frequency deviation and your signal bandwidth. We can write down as 2 beta plus 1 FM.
What's the range for that? What's the range for
There is no hard threshold for what is huge, what is small. So in exam, I'm going to give you a big number, really big, right? And a small. For example, there's really no such which one I consider big, which I consider small. Small, there is a hard threshold, less than 0.2. So if you really want to know the accurate bandwidth, you use significant sideband. Those two give you approximately right bandwidth with using really quick sideband. So just give you some idea, right, how wide it is. So there's nobody says 6, you use this one. But generally, when beta is big, right, those two will be very close, very close. If you're not sure, use cursor through. Okay, if you are really not sure, right, use cursor, like beta is 5, 7, 8, something like that, right? If beta is 100, definitely it's large one.